so again, this is the most general situation. Now, if the function is special, now another question is, when do we have equality? Well, we need a special function. For example, the top will have equality if the function is 1-to-1. The bottom will have equality if the function is onto or surjective. 1-to-1 means injective, onto means surjective. And so when a function is both 1-to-1 and onto, it has a special name, an injection, injective and surjective. How do we call those functions? Bijective. When a function is bijective, then we have equality in both cases. You can go back and forth however you want. And that's when the inverse function exists. Okay? That inverse function that you used to find in college algebra and so on and pre-calculus, that only happens, that function only exists when your function is both injective and surjective. When it's a bijection. Okay? That's the best case scenario. You can go back and forth however you want. Okay? You don't lose or gain any information by looking at images or inverse images. But when your function is general, this is the best that we can hope. Did you understand this? Again, take your time later on looking at this again. And this just requires you to understand, what do we really mean by this? What do we really mean by this? That's all that's happening here. Okay? Definition, that's all that's happening. All right. Questions? No? Okay, so we cleared that up. Now, let's see. Let's call that one number 1. Okay, that was our first question. Second question. That's just, you know, how the two operations relate with each other. Now, another natural question to ask is, how do these operations of image and inverse image behave with respect to unions and intersection? Okay? So, for example, you have your function from A to B as usual. Let's think about the image first. And then let's say you have S and T. They are both subset of A. Okay? Then, of course, the union is still a subset of A. Yes? So, a natural question is, what can we say about, you know, you can look at the image of the union, but you can also look at the image of S and the image of T, you know, individually, and then look at their union. What can we say about these guys? What goes in the box? Do we get equality? Is it true that the image of the union is the union of the images? Or do we gain or do we lose something? What's going on here? Okay? And then we want to say a similar thing with respect to the inverse image, and then same sort of question for intersections. Okay? All right, let's see. Let's take a look at this one. So once again, let's give it, usually if you have no idea, then let's just give it the benefit of the doubt. Let's try to prove that they are equal. So how do we do that? Start with an element here, argue that's on the other side, and the other way around. Okay? So let's see. So okay, what letter should I use? Where are we playing? In what set are we playing? Are we playing inside A or are we playing inside B? Look at the statement. What are we dealing with? We're dealing with images. Where do the images live? In B, right? Do you understand this? This guy is in B, it's a subset of B. Right? Yes, S and T are subset of A. Yes, but when I apply the function, when I look at their image, this already was translated into B. Okay? So again, don't use misleading letters. Little b. So that you can also track yourself where you are. So then let little b be an element in the image of S union T. Okay? Now let's activate the process. What does this mean? What does it mean to be an element in the image? It means that there is a little a back home, so that when you apply the function, it gives you this b. That's what it means to be in the image, right? There is an element in A, so that when you apply the function, it gives you b. Moreover, it's not just in A, in this set, in the union, in this special union, right? So then, and again, when I say then, it means this follows by the definition, okay? So then, there exists an A in the union, such that when I do f of A, I get b. That's That's what it means to be an element in the image. Okay, that's the definition of the image. All right, so we have this element in the union. Now remember, this is what you want to say, right? Now, well, this is pretty straightforward because now from here, what can we deduce? So I guess instead of writing paragraph, I think it works better if I do things formally. So let B be an element in the image, then there exists an A in the union, such that f of A equals f of B, and then here I use definition. Because now we're going to play with a little bit of logic. So that was definition of image. Okay? All right. Now what am I going to say? I'm going to use the definition of union. If A is in the union, what does that mean? You don't know. So what does it mean to be in the union? What's the definition of union? So how do we say it? Very good. You need to use or, not and. If you say both, then that means and. Yes, that will be intersection. So then from here it follows that A is in S or A is in T. Okay? So now to break it up, remember, it means that A is in S or in T, but now we have this extra information about A. So now we can break this down completely into logic and say and f of A equals B. Do you understand this? Remember, these are two things that are happening simultaneously. A is in the union, and it also happens that when you apply f of A, you get B. Understand this? So then I want to get down to logic. So, all right. So what we used in this step was definition of union. This is what you understand. Now, what am I going to do? I'm going to distribute, right? I'm going to distribute and over or. So then this means A is in S and f of A equals B, or A is in T and f of A equals B. Yes? I just distributed this guy. Oh. Okay. So this is, I'm just going to call it logic. Now what we used was distributive property, one of the standard, the basic logical equivalences. Okay. Now let's read this parenthesis. What does this mean? A is in S and f of A equals B. What does that mean? What can we say from this parenthesis? Remember what we want. Look at, always don't lose track of what we want. Can we now argue that B belongs to the image of S? Is this enough to say that B is an element of the image of S? That's exactly what it means. Because there is an element in S, so when you apply the function, it gives you B. In other words, B belongs to the image of S. It's a result of doing f of something from S. Okay? So that first parenthesis tells me that B belongs to the image of S. Okay? Or, now similarly, what does the second parenthesis tell me? That B belongs to the image of T. Right? Because in the second parenthesis is telling me that B is a result of doing f of something from T. So it's in the image. Okay? Here we use definition of image. But then, if B is in this set or in this set, where is it? In the union. Then B is in the union. That's the definition of union. Did you understand this? So we just argue that if you start with an element in the union of the image, in the image of the union, then that element belongs to the union of the image. Okay? How about the other way around? So let's see, can we trace back our steps? Can we reverse these arguments? This cannot always be done, but in this case, can we do it? My advice to you, that's why I did it this way, so I don't have to then write the second paragraph. Look at your justifications. If your justifications are entirely, do not use any assumption, nothing. If your justifications are entirely definitions and logical equivalences from logic, then this is fully reversible because definitions, they work back and forth. Okay? In other words, let's read it and see if it makes sense. To prove the other direction would be to start with an element on the right and show that it's on the left. So, this bottom line. Suppose that we start with B in here. Does that mean then that B is in either the image of S or the image of T? Well, yes, that's the definition of union. So, this naturally can be reversed. Now, can we then deduce the next line? Okay, if B is here, that means that there's an A in S, so when I do f of A is equal to B. Yes? So certainly this parenthesis makes sense. You will just need to put it that exists here. But it's there. So if we say A, it's because there exists an A. And then similarly, this one translates into this. That's the definition of being an image. Okay? This B is the result of doing f of something coming from T. Okay? So we have this line. Now here, what happens from here to here? Who can tell me what's happening from this step to this one? What is it? So you are reversing the distributive property. How is that called? How do you call that in college in algebra? How do you call that? Factoring. What we just did here is factoring. When you factor something, when you factor the GCF, the greatest common factor, what are you doing? You are reversing the distributive property, right? I mean, if you have if you have 2x squared plus 4x, you want to factor this, what do? You take out 2x, and then what do you have? So let me do this. So then what do you have? Or actually, yeah. Then you have x here and then a 2. But basically, what did you just do? You reverse the distributive property. What is the distributive property? This is 2x times x plus 2x times 2, right? And what you did was you went back. That's what factoring is, when you factor out a common factor. That's exactly what we did here. Imagine that this is your times and this is your plus. Okay? Here is your plus and here are your times. We have the same thing being multiplied in both things, then you factor it out. So that's just factoring. But it's not plus of times, it's the logical connectors. Okay. And then once you are here, then of course this parenthesis turns into this one, right? Because that means that it's in the union. And then A is in the union, and f of A equals B. That certainly means that then B is in the image because it's coming from somebody in the union. When you apply that, okay? So it's fully reversible. So indeed, both sets, they have the same element. That's what we just showed, okay? So the image of the union equals the union of the images. Nothing weird happens here. Do you understand this? Okay, so let's see. Let's do inverse image. Let's see, why don't you try it? So then let's call this one, okay, number 3 now. Again, f goes from A to B. Now this time, we want to see how inverse image behave with respect to union. So we need to take two subsets of B. So let S and T be subsets of B now. Okay. Then what can we say about? So again, you can consider the union, the union of S and T. That will be a subset of B. You can pull it back to A. So what can we say about this? Pull back S first, pull back T, and then collect them in A. Okay, so here what we're doing is we're collecting them in B, and then we're pulling the entire thing back to A. Here what we're doing is we're pulling back a piece, pull back S, pull back T, and then collect them together in A. The question is, do we get the same thing? Okay, doesn't really matter when you collect. Okay, so again, I suggest give it the benefit of the doubt. Try to see if you can prove it. If you get stuck, what do I mean by getting stuck? If you get to a step in which you cannot logically continue, then maybe you start to suspect, probably this is not true, and then you try to look for a counterexample. And that place that you're getting stuck, that's the one that we suggest what sort of counterexample you need. Okay? So, you will try. Let me take attendance. Daniela Áviles, Andy Brito, Raúl Campos, Brian Cruz, Miguel Díaz, Brian Echevarría, Anthony Fuentes, Ian German, Talía González, Carlos González, Sebastián González, Alejandro Iscaray, Alfredo Llanes, Edwin Mendieta, Mario Núñez, Leonardo Quevedo, Michael Valdez. Okay. So Miguel, remember, even if you are online, that does not count as attendance. All right, so let's see, what do you think? Does equality hold? Let's see, let's just do it. So how do we begin? What letter should I use? A or B? Which one is it? Letter A. Does everyone understand this? We're pulling back, so we are inside A. So little a. So let little a be in the inverse image of S union T. Okay, then what does this mean? So what's the definition of inverse image? This is just definitions. That's all it is. Definitions. Think about the picture. That's why I draw the pictures for you. What does that mean? It means that if I apply F, if I apply F to A, what do I get? Where do I go? I know it goes to B always, but does it go to a special place? What do we know? That's the reason why we call it inverse image. F of A goes in here, in the union. It doesn't go anywhere else. I mean, that's what it means, right? Yes, I know it goes into B. B is the whole thing, okay? But, you know, it means that it goes into the union. It's the definition. That means that if I do F of A, it belongs to the union. Look at the picture, guys. I don't know why this is confusing. You have a subset of B. Let's call it T. And you apply the inverse image that produces this set. What's the property of this set? Look at the picture. If I do F to any element here, where do they go? T. Right? So when you do the inverse image of something, that means that will give you something here in A, so when you apply the function, it goes into this something. All right? That's what it means. Okay. All right, so that's definition of inverse image. Okay? All right, now what can we do? Again, always remember, somehow we want to narrow it down to inverse image of S and also narrow it down to inverse image of T. So that's our goal. So what can we do from here? There's only one thing we can do. So what can we do? Say that again. Use definition of union. What can you say from here? Or. This is very important. Okay, so then this means that F of A is in S or in T. I mean, it could be one of the two. We don't know, right? So you have to consider both cases. It's either in S or in T. Here we use definition of union. Yes? All right, now, what can we say? F of A is in S. What does that mean? What can we say about A? A is an element that when you apply the function, it goes into S. So what can you say about A? No, F of A is in S. So what can I say about A? Here is B, here is S, in this way, and then somehow there is an A here that goes in S. That's what's happening, right? That's what we have right now in there. What can you say about this A? Does it belong to any special subset of A? If I do the inverse image of S, will it contain A? Yes, of course. I mean, that's what it means. These are all the elements in A that goes to S. Yes? Do you understand this? So this is telling me that A, when I apply the function, goes into S. Well, that's what it means for A to be in the inverse image of S. That's what it means. That when I do f of A, it's an element of S. Yes? Or, what would be the other possibility? It's in the inverse of T. Yes? One of the two. So what do we use here? Definition of inverse image, right? But if it's here or in here, where is it? The union. That's exactly what we want, right? Here we use definition of union. Yes? So we just showed that the left is a subset of the right. That's what we just showed. Now, can we reverse the arrows? Can the arrows be reversed? Yes. Look at your justification. Here, everything is just definitions, right? So all of these things are equivalent statements. So you can certainly go back. So these two sets, they have the same end. So we conclude that the inverse image of the union equals the union of the inverse image. So moral of the story, union is a very nice operation with respect to these two concepts. So these two concepts of image and inverse image, they behave well on the union, okay? You don't lose or gain anything. They distribute nicely. What do you think is the next question that you need to think about? How do they behave with intersection? Intersection is not that nice, okay? So, so let me give you this as a homework for you to think. So homework, how about intersection? So here is a hint. I mean, it's harder if I don't tell you what's going to happen and you have to investigate it on your own. Do you want that, or would you rather tell me what it is and then you just verify it? Let's see. So just verify. And Monday we discuss it. But take your time, because why it is important? Because this allows you to really understand the concepts. Okay? So that when these things come up, then you know exactly what needs to be done. Okay? So how about intersection? So the question is, you know, how does the image of S intersection T behave with respect to the intersections of the images? And the other question is, you know, same thing for, of course, in each of them, you need to understand here is a subset of A and this one is a subset of B, okay? So make sure that you made the proper adjustments. So what's the relationship? Containment, equality, just like with the union, what happens? What goes in the mystery box, okay? All right, so we stop. We went over too much. Okay, do you guys have any questions? No questions?
You told us to solve one of the questions. You told us to solve. I don't understand how to solve it.
Which one?
It was the image. You know the intersections. You told us to do? Yeah, it was one of those.
Which one? The image or the inverse image?
The image.
Remember, I asked you for two of them.
Yeah,
So the first one, the image of the intersection.
Yeah.
Just plot that. Okay. All right. So let's see. Let's take a look at this. So solution part A. So we want to figure out, what's the relationship between the image of the intersection and the intersection of the images. Okay. So let's see. For example, let's give it the benefit of the doubt. Okay, and let's see if we can prove whether they are equal or not. If we cannot, meaning if we get stuck at some point, then most likely that's not. Most likely they will not be equal, but we will see. So in this setup, because we're talking about image, remember f is a function from A to B, and then S and T, they're both subsets of A. Okay, and then we're looking at their images inside B. The image is a subset of B. Okay, so let's see. Let us try to see if we can show this. In other words, the question is, can we somehow argue that the image of the intersection is a subset of the intersection of the images? Okay. All right. So I'm going to start with an element over here and try to see if we can argue that that element belongs on the other side. So because that's a subset of B, I'm gonna use lowercase. Okay. So let lowercase b be an element in the image. Okay. So what does this mean? So then this means that there exists an A, right, inside this intersection. So when I do f of A, I get this B. In other words, to be an element in this image means that this B is the result of doing f of something that lives inside this set. That's what it means. Okay, B has a pre-image in the intersection. So that means there exists an A in the intersection such that f of A equals B. So let me translate what this is. So that means we have A's in the intersection and f of A is equal to B. That's what we have so far. Okay. And this is just definition of image. So what we're using here is definition of image. Now I'm going to carry on the definition of intersection. This tells me that A is both in S and T. So then from here it follows that A is in S and A is in T. And then we also have the condition that f of A is equal to B. Now certainly, like we did before, we can replicate this, we can repeat this guy, and then because everything is and, we can just thread it together. So basically, so here we use definition of intersection. Okay, so then from here it follows that A is in S and f of A is in B, and we have that A is in T and f of A is in B. Okay, so here that was just a logic step. What I did was, I repeated this one twice, and then I put this one with the first one, and then the same copy of it with this one. Now this tells me that there is an element in S, so that when you apply the function, it gives you B. So that essentially means that B is in the image of S. Okay, that's what it means. And then the other parenthesis is telling me that there is an element in T. So that when you apply the function, you get B. So that means B is in the image of T. Do you understand this? Yes? So from here it follows then that B is in the intersection. So let's see, this one was a logic step. This one here was definition of image. And this one here is definition of intersection. Okay? So let's take a look at it again. So B is in the image of the intersection. That means that there exists an element in S intersection T, such that when I do f of A, it gives me B. That's the definition of image. So it has a pre-image inside this set. That's what we're saying there. Now I'm just rewriting that first line in here. Okay? So that means that we have A in the intersection and f of A equals B. Now break it up using definition of intersection, and then when you pair this guy together with this one, then we get these two statements. A is in S and f of A equals B, and we also have that A is in T and f of A equals B. So now looking at this parenthesis, this tells me that B is in the image of S because it's the result of doing F of something coming from S. And this tells me that B is also in the image of T because it's the result of doing F of something coming from T. So it is in both places, it's in the intersection. So this proof have no issues. So that means, let me put here, yes, so far, okay? So far we have that the image of the intersection is a subset of the intersection of the images, okay? So let me say that. So the image of the intersection is a subset of the intersection of the images. Now the question is, can we reverse this? Let's see. Let's start with an element in the intersection. Okay, so that means that B is in the image of S and B is in the image of T. So this arrow can be reversed, no problem. Okay. Now here is the issue. Okay. When you go from here to here, okay, you have to be very careful because there are two statements here. This one certainly gives you this statement. If B is in the image of S, that means that there exists an A in S for which f of A equals B. So this gives you this. Now this one, what does this mean? This means there exists an element in T for which f of that element equals B. But nobody guarantees that the element that we're using here in T is the same one as the one that we're using here. You see, it could be that this is because there is an element in S, so that f of that element gives me B, and then this one could be because there is an element in T, so that when you apply F, it gives you B as well. In other words, what I'm saying is, you have a situation, you could have a situation like this. Imagine a function in which you have a situation like this. And by the way, this is how we're going to construct a counterexample. And then this is your S, and this is your T. You could have a function that does this, that has this situation. So when you go from B is an element of the image of S, okay, yes, because it's the image of S. Let's say S only has this element, okay. Then yes, okay, there exists an element in S, so that f of that element gives me B. That's this guy. But then on the other parenthesis, B is an image of T. That's because there is another element, most likely, okay, could be, that belongs to T, so when you apply the function, gives you B. But these two guys don't have to be the same. You see that? And that's the problem. That's why we cannot say that this implies the line above, because the A that we're using here is not the same as this A. Okay? When we came this way, that was fine because we started by saying that that A was in the intersection, and therefore that A is the same in both places. Okay? That's why we can manage to show this inclusion. But if you try to do it the other way, it's not going to work because from here to here it breaks immediately. Because what you could say to go from this step to this one is that there is an A1 in here and there is an A2 in here. But there's no guarantee for you for A1 and A2 to be the same. Here is a situation in which that can happen. Okay? So notice how we can see, that's why you have to be very careful. If I try to prove the other way, I see that I get stuck because I cannot actually get past this step. But the fact that I'm getting stuck is telling me how to construct the counterexample. I need to now provide a counterexample to say the other way doesn't work and tell you a concrete example. And here's a picture of what we're going to use. Okay? This allows you to build the counterexample. So this doesn't work. So you could reverse here nicely, but then if you try to go from here to here, it's not going to work. And we're going to build on this for that. Okay? So claim the intersection of the images is not a subset of the image of the intersection. Okay? Now, of course, to argue this, you need to produce a counterexample. I'm just going to keep it as simple as possible. So let's take a look at that picture over there, and then let's just make it work like so. So let's say A is a set 1, 2. Okay? Let's say B is a set 3. Okay? And then we're going to define our function f from A to B. You know, just 1 goes to 3, 2 goes to 3. Right? Both of them goes to the same value. In other words, remember, this means f of 1 equals 3, f of 2 equals 3. Okay? That's how we're defining the function. And then S is going to be the set containing 1, and T is going to be the set containing 2. and then T is a set containing 2. They are both subsets of A. Now that we have all the elements in place, let us compute. To argue this, what you have to do is compute the left, compute the right, and show that they're not the same. Okay? So we need S intersection T. What's S intersection T? What is it in this case? What is it? The empty set. Good. That's the empty set. So now let's compute what we need. So what's the image? What's the image of S? The image of S is 3. What's the image of T? 3. Therefore, now we can compute this part. So what's the intersection? What's the intersection? What's the intersection? 3. I mean, this set has 3. This set has 3. What do they have in common? 3. Yes. So intersection is 3. Okay. So now, on the other hand, what's f of the intersection? What's the image of the intersection? Well, the intersection was empty. So what's the image of the empty set? We talked about this at the very beginning when we talked about image. What's the image of the empty set? It's the empty set. Because if it's not the empty set, what you're telling me is that then there is an element that has a pre-image in the empty set, but the empty set has no element. So there's no way that something from the empty set will give you a non-empty set as an image. Okay? So now you can clearly see that these two things are not the same. So these two guys are different from each other. Okay? Notice that even in this example, we do get that the image of the intersection is a subset of this. Why? Because the empty set is a subset of everybody, which is what we proved above, right? Above, we proved that the other way around always works. This, the image of the intersection, is always a subset of the intersection of the image. And that's not being violated here, because the empty set is a subset of this guy. But what we don't have is that this guy being a subset of this one. Let me say, since the set containing 3 is not a subset of the empty set. Okay? And that's what our claim was. So this is our counterexample. Now, if you don't like the empty set, you can cook the example so that there is no empty set. If it makes you uncomfortable to do the empty set, then just cook the example. Remember, your example has to have this feature. It cannot be, let's see, what property of a function is being violated here? It's what we're going to talk about today, but I saw that most of you already did the homework on this, so you should know. What property is being violated here? This is a function. What property is being violated? The one-to-one function, right? So if a function, this function is now one-to-one, and that's when this thing is going to fail, okay? So if you want to cook another example, another counterexample, make sure that you give me a function that is now one-to-one. If you do something one-to-one, it's going to work, okay? One-to-one functions are nice. So make sure that you give me something that's now one-to-one. So I'm telling you this because maybe you don't like the fact that it was empty. Then you have to deal with this empty set business, okay? You are free to cook whatever example you want. So let's see. Let me show you how we can cook it up a little bit differently. So another, along the same lines, but then of course now I have to make my A a little bit bigger. So let's do A being 1, 2, 3, and then let's say that B doesn't really matter. We could just have everybody going to 4, and then because then we have intersection. Let's do here 4 and 5, and then let's see, my function is better to just have a picture. So here is A, here is B. We want F to go like this. So 1, 2, 3, 4, 5. So I'm gonna send 1 to 4, 2 to 4, and then 3 to 5, and then I'm gonna make. Let me do it the other way. 2 to 5, and then 3 to 4. Okay, so then this is gonna be S, and then this is gonna be T. Remember, you have to cook it in such a way that we have that situation that if you take an element in B, then when you go back, it's coming from one guy in A, but it also could come from one guy in T that are different. Okay, that was the essence of what was of the problem that we saw here. Okay, that's what I'm just trying to make up. Okay, so that means with this construction, our S is 1, 2, and our T is 2, 3. All right, so this time we have a non-empty intersection. So what's the intersection? So it's 2, okay. So intersection is 2. So let's compute what we need. So what's the image of S? 4, 5. What's the image of T? 4, 5 as well. Good. So what's f of S intersected with f of T? 4, 5. Okay. And now what's the image of the intersection? Remember, the intersection was a set 2. So what's the image of 2? 5. So certainly this guy is a subset of this one. That's what we proved before. Okay. And now what we're trying to see is the top a subset of the bottom. So what can we say here? So we can clearly see that the intersection of the images is not a subset of this guy. In this case, it's larger, right? Because this one has a 4 and this one doesn't. Okay. Notice that the other way around, yes, it will always contain it. That's what we proved. Okay. But the other way around doesn't work. So, moral of the story, what we just did was the proof of the following theorem. When it comes to images, what we have is that the image of the intersection is a subset of the intersection of the image. This is what we can say in all cases. Okay. Sometimes we do have a nice equality, but the function has to be special. It has to be 1-to-1 and have, it has to be a special function. But for an arbitrary function, we just put 2 different counterexamples. Okay. But notice that the key fact here is that the function cannot be 1-to-1 if you want this to work. If you want to build your counterexample. So good. That's a hard one because this one, if you did it, then you should check that it works. Okay. So inverse image is very nice. It's very nice with respect to union, as we saw before. Okay. Inverse image works very nice with unions, and it also works very nice with intersection. Now the image is the one that is a little bit troublesome. It surprisingly behaves well with respect to union, the image, but when it comes to intersection, it doesn't work that well. What you can say here is subset. Okay, that's what you can say. Good question. Did you understand? So, good. So remember, every time that you think that something doesn't work, then what you need to do is cook up a counterexample. Okay, so you can justify. You have to give me something concrete. Counterexample is you need to give me an A, you need to give me a B, you need to give me a function, the rule that defines the function, and then your S and your T with all the necessary properties. Okay. Good. All right. Questions? Okay, great.